Hey everyone, welcome back to our new video. So in this video we are going to start the introduction to quantum technologies and applications subject. So by our previous video we have completed the computer networks and internet protocols first unit. So I'll be tagging the complete playlist so you can check out later. If you are new to JNTUX concepts, don't forget to subscribe and like this video. So let's get into our very first topic, that is the transition from classical to quantum physics. Transition from classical to quantum physics. That is the first topic in introduction to quantum applications and technologies. So before directly getting into the actual topic, we should know what is meant by classical physics. Classical physics is a branch of physics which deals with the laws of motion, forces, energy, and fields at the macroscopic level. So it deals with the motions, force, energy, etc. physics concepts at a macroscopic level. It is deterministic and continuous. It is an important point. The classical physics is deterministic and continuous in nature. We have theories like Newtonian mechanics, Maxwell electromagnetism as an example for classical physics. But meanwhile, what is meant by quantum physics? As this entire subject revolves around the quantum. So, quantum physics or quantum mechanics is a branch of physics that explains the nature at a very small scale, like atoms, photons, nucleus, protons, etc. Quantum physics works in the area where the classical physics fails. We know that classical physics works at the macroscopic level, but the quantum physics works in the microscopic level. It is probabilistic and quantized in nature. We have example theories like quantum mechanics, quantum field theory, etc. So now the transition from classical physics to quantum physics, how the transition happened, what was the cause for this transition? All these questions can be clarified now. So at the end of 19th century, classical physics was nearly complete and progressed to a level that scientists thought all problems are solved or were about to be solved, because the classical Newtonian mechanics was able to predict the motion of planets. Electromagnetism was explained by Maxwell's equations. Thermodynamics clarified the heat and work, and classical optics enabled scientific tools like telescopes and microscopes. Everything was seemed to be perfect, and all those theories helped to develop the physics principles in a great way. But whereas in chemistry, it had the basic periodic table, but the atomic structure and electron behavior in reactions were not understood. Likewise, in classical physics, dominated for over centuries, but Rutherford experiments revealed that atoms that had dense, positively charged nuclei with orbiting electrons providing negative charge, which raised questions that classical physics failed to explain due to the predicted energy loss. There were other such phenomena like black body radiation, hydrogen spectral lines, molecular spectroscopy, photoelectric effect, uncertainty principle, Schrodinger principle, etc. All these principles or phenomena together contributed to expose the limitations or drawbacks of classical physics. As the experiments grew more precise to the atomic and subatomic levels, the cracks were about to begin to rise, and all these led to the development of new theoretical concepts. So, that theoretical concept is nothing but quantum mechanics or quantum physics. So in the year 1920, the formulation of quantum mechanics took place. Various scientists like Planck, Heisenberg, Bohr, de Broglie, Schrödinger, etc. are linked to the new theoretical models. Quantum mechanics or quantum theory redefined the complete understanding of reality. It occupied hundreds of publications and letters. It was accurate and predictive incredibly. Quantum theory provided the foundation for semiconductors, lasers, nuclear energy, etc. As the time evolved, it also played a key role in the quantum technologies. Quantum technologies like quantum computing, quantum cryptography, quantum sensing, etc. domains. The ultimate transition from classical to quantum mechanics is marked as the one of the most profound evolution of scientific knowledge in the scientific history. So this is the first topic in the IQTA subject. So this particular subject is going to be more on theoretical side. So that's it for this video. I hope you have understood the concept of transition from classical to quantum physics. In our next video, we are going to discuss the second topic of IQTA, that is the fundamental principles explained conceptually, like superposition, entanglement, uncertainty principle, wave particle duality. All these four fundamental principles or phenomena are discussed in the upcoming videos. So until then, keep learning and don't forget to subscribe.